The alkali metals are a group in the periodic table consisting of the chemical elements lithium, sodium, potassium, rubidium, caesium, and francium. This group lies in the S block of the periodic table of elements, as all alkali metals have their outermost electron in an s-orbital. This element-electron configuration results in their characteristic properties. The alkali metals provide the best example of group trends in properties in the periodic table, with elements exhibiting well-characterized homologous behavior. The alkali metals have very similar properties. They are all shiny, soft, highly reactive metals at standard temperature and pressure, and readily lose their outermost electron to form cations with charge +1. They can all be cut easily with a knife due to their softness, exposing a shiny surface that tarnishes rapidly in air due to oxidation by atmospheric moisture and oxygen. Because of their high reactivity, they must be stored under oil to prevent reaction with air, and are found naturally only in salts and never as the free element. In the modern IUPAC nomenclature, the alkali metals comprise the group 1 elements, excluding hydrogen, which is nominally a group 1 element but not normally considered to be an alkali metal, as it rarely exhibits behavior comparable to that of the alkali metals. All the alkali metals react with water, with the heavier alkali metals reacting more vigorously than the lighter ones. All of the discovered alkali metals occur in nature. In order of abundance, sodium is the most abundant, followed by potassium, lithium, rubidium, caesium, and finally francium, which is very rare due to its extremely high radioactivity and thus occurs only in traces due to its presence in natural decay chains. Experiments have been conducted to attempt the synthesis of untitled, which is likely to be the next member of the group, but they have all met with failure. However, untitled may not be an alkali metal due to relativistic effects, which are predicted to have a large influence on the chemical properties of superheavy elements. Even if it does turn out to be an alkali metal, it is predicted to have some differences in physical and chemical properties from its lighter homologs. Most alkali metals have many different applications. Two of the most well-known applications of the pure elements are rubidium and caesium atomic clocks, of which caesium atomic clocks are the most accurate and precise representation of time. A common application of the compounds of sodium is the sodium vapor lamp, which emits very efficient light. Table salt, or sodium chloride, has been used since antiquity. Sodium and potassium are also essential elements, having major biological roles as electrolytes. And although the other alkali metals are not essential, they also have various effects on the body, both beneficial and harmful properties. Physical and chemical. The physical and chemical properties of the alkali metals can be readily explained by their having an ns1 valence electron configuration, which results in weak metallic bonding. Hence, all the alkali metals are soft and have low densities, melting and boiling points, as well as heats of sublimation, vaporization. In dissociation, they all crystallize in the body-centered cubic crystal structure, and have distinctive flame colors because their outer s-electron is very easily excited. The ns1 configuration also results in the alkali metals having very large atomic and ionic radii, as well as high thermal and electrical conductivity. Their chemistry is dominated by the loss of their lone valence electron to form the +1 oxidation state. Due to the ease of ionizing this electron and the very high second ionization energy, most of the chemistry has been observed only for the first 5 members of the group. The chemistry of francium is not well established due to its extreme radioactivity, thus, the presentation of its properties here is limited. The alkali metals are more similar to each other than the elements in any other group are to each other. For instance, when moving down the table, all known alkali metals show increasing atomic radius, decreasing electronegativity, increasing reactivity, in decreasing melting and boiling points, as well as heats of fusion and vaporization. In general, their densities increase when moving down the table, with the exception that potassium is less dense than sodium. One of the very few properties of the alkali metals that does not display a very smooth trend is their reduction potentials. Lithium's value is anomalous, being more negative than the others. This is because the Li+ ion has a very high hydration energy in the gas phase. Though the lithium ion disrupts the structure of water significantly, causing a higher change in entropy. This high hydration energy is enough to make the reduction potentials indicate it as being the most electropositive alkali metal, despite the difficulty of ionizing it in the gas phase. The stable alkali metals are all silver-colored metals except for caesium, which has a golden tint. It is one of only 3 metals that are clearly colored. Additionally, the heavy alkaline earth metals calcium, strontium, and barium, as well as the divalent lanthanides europium and ytterbium, are pale yellow, though the color is much less prominent than it is for caesium. Their luster tarnishes rapidly in air due to oxidation. They all crystallize in the body-centered cubic crystal structure, and have distinctive flame colors because their outer s-electron is very easily excited. All the alkali metals are highly reactive and are never found in elemental forms in nature. Because of this, they are usually stored in mineral oil or kerosene. They react aggressively with the halogens to form the alkali metal halides, which are white ionic crystalline compounds that are all soluble in water except lithium fluoride. The alkali metals also react with water to form strongly alkaline hydroxides and thus should be handled with great care. The heavier alkali metals react more vigorously than the lighter ones. For example, when dropped into water, caesium produces a larger explosion than potassium. The alkali metals have the lowest first ionization energies in their respective periods of the periodic table because of their low effective nuclear charge and the ability to attain a noble gas configuration by losing just one electron. The second ionization energy of all of the alkali metals is very high as it is in a full shell that is also closer to the nucleus, thus, they almost always lose a single electron, forming cations. The alkaloids are an exception. They are unstable compounds which contain alkali metals in a -1 oxidation state, which is very unusual as before the discovery of the alkaloids, the alkali metals were not expected to be able to form anions and were thought to be able to appear in salts only as cations. The alkalide anions have filled s subshells, which gives them more stability and allows them to exist. All the stable alkali metals except lithium are known to be able to form alkalides, and the alkalides have much theoretical interest due to their unusual stoichiometry and low ionization potentials. Alkalides are chemically similar to the electrides, which are salts with trapped electrons acting as anions. A particularly striking example of an alkalide is inverse sodium hydride, H plus Na minus, as opposed to the usual sodium hydride, Na plus H minus. It is unstable in isolation, due to its high energy resulting from the displacement of 2 electrons from hydrogen to sodium, although several derivatives are predicted to be metastable or stable. In aqueous solution, the alkali metal ions form aqua ions of the formula Mn+, where N is the solvation number. Their coordination numbers and shapes agree well with those expected from their ionic radii. In aqueous solution, the water molecules directly attached to the metal ion are said to belong to the first coordination sphere, also known as the first, or primary, s-orbital shell. The bond between a water molecule and the metal ion is a dative covalent bond, with the oxygen atom donating both electrons to the bond. Each coordinated water molecule may be attached by hydrogen bonds to other water molecules. The latter are said to reside in the second coordination sphere. However, for the alkali metal cations, the second coordination sphere is not well defined as the +1 charge on the cation is not high enough to polarize the water molecules in the primary solvation shell enough for them to form strong hydrogen bonds with those in the second coordination sphere, producing a more stable entity. The solvation number for Li+ has been experimentally determined to be 4, forming the tetrahedral Li4+, while solvation numbers of 3 to 6 have been found for lithium aqua ions. Solvation numbers less than the fourth may be the result of the formation of contact ion pairs, and the higher solvation numbers may be interpreted in terms of water molecules that approach Li4+ through a face of the tetrahedron. Though molecular dynamic simulations may indicate the existence of an octahedral hexaaqua ion, there are also probably 6 water molecules in the primary solvation sphere of the sodium ion, forming the octahedral Na6+ ion. While it was previously thought that the heavier alkali metals also formed octahedral hexaaqua ions, it has since been found that potassium and rubidium probably form the K8+ and Rb8+ ions, which have the square antiprismatic structure, and that caesium forms the 12-coordinate Cs12+ ion. Lithium. The chemistry of lithium shows several differences from that of the rest of the group, as the small Li+ cation polarizes anions and gives its compounds a more covalent character. Lithium and magnesium have a diagonal relationship due to their similar atomic radii, so that they show some similarities. For example, lithium forms a stable nitride, a property common among all the alkaline earth metals but unique among the alkali metals. In addition, among their respective groups, only lithium and magnesium form covalent organometallic compounds. Lithium fluoride is the only alkali metal halide that is not soluble in water, and lithium hydroxide is the only alkali metal hydroxide that is not deliquescent. Conversely, lithium perchlorate and other lithium salts with large anions that cannot be polarized are much more stable than the analogous compounds of the other alkali metals, probably because Li+ has a high solvation energy. This effect also means that most simple lithium salts are commonly encountered in hydrated form, because the anhydrous forms are extremely hygroscopic. This allows salts like lithium chloride and lithium bromide to be used in dehumidifiers and air conditioners. Francium is also predicted to show some differences due to its high atomic weight, causing its electrons to travel at considerable fractions of the speed of light and thus making relativistic effects more prominent. In contrast to the trend of decreasing electronegativities and ionization energies of the alkali metals, francium's electronegativity and ionization energy are predicted to be higher than caesium's due to the relativistic stabilization of the 7s electrons. Also, its atomic radius is expected to be abnormally low. All known physical properties of francium also deviate from the clear trends going from lithium to caesium, such as the first ionization energy, electron affinity, and anion polarizability. The CsFr molecule is also polarized as Cs plus Fr-, showing that the 7s subshell of francium is much more strongly affected by relativistic effects than the 6s subshell of caesium. Additionally, francium superoxide is expected to have covalent character, unlike the other alkali metal superoxides, because of bonding contributions from the 6p electrons of francium. Nuclear. All the alkali metals have odd atomic numbers, hence, their isotopes must be either odd-odd or odd-even. Odd-odd nuclei have even mass numbers, whereas odd-even nuclei have odd mass numbers. Odd-odd primordial nuclides are rare because most odd-odd nuclei are highly unstable with respect to beta decay, because the decay products so even, and are therefore more strongly bound, due to nuclear pairing effects. Due to the great rarity of odd-odd nuclei, almost all the primordial isotopes of the alkali metals are odd-even. For a given odd mass number, there can be only a single beta-stable nuclide. Since there is not a difference in binding energy between even-odd and odd-even comparable to that between even and odd-odd, leaving other nuclides of the same mass number free to beta decay toward the lowest mass nuclide. An effect of the instability of an odd number of either type of nucleons is that odd-numbered elements, such as the alkali metals, tend to have fewer stable isotopes than even-numbered elements. Of the 26 monoisotopic elements that have only a single stable isotope, all but one have an odd atomic number and all but one also have an even number of neutrons. Beryllium is the single exception to both rules, due to its low atomic number. All of the alkali metals except lithium and caesium have at least one naturally occurring radioisotope. Sodium-22 and sodium-24 are trace radioisotopes produced cosmogenically. Potassium-40 and rubidium-87 have very long half-lives and thus occur naturally, and all isotopes of francium are radioactive. Caesium was also thought to be radioactive in the early 20th century, although it has no naturally occurring radioisotopes. The natural radioisotope of potassium, potassium-40, makes up about 0.012% of natural potassium, and thus natural potassium is weakly radioactive. This natural radioactivity became a basis for a mistaken claim of the discovery for element 87 in 1925. Caesium-137, with a half-life of 30.17 years, is one of the two principal medium-Lv fission products, along with strontium-90, which are responsible for most of the radioactivity of spent nuclear fuel after several years of cooling, up to several hundred years after use. It constitutes most of the radioactivity still left from the Chernobyl accident. 137 Cs undergoes high-energy beta decay and eventually becomes stable barium-137. It is a strong emitter of gamma radiation. 137 Cs has a very low rate of neutron capture and cannot be feasibly disposed of in this way, but must be allowed to decay. 137 Cs has been used as a tracer in hydrologic studies, analogous to the use of tritium. Small amounts of cesium-134 and cesium-137 were released into the environment during nearly all nuclear weapon tests and some nuclear accidents, most notably the Goiânia accident and the Chernobyl disaster. As of 2005, cesium-137 is the principal source of radiation in the zone of alienation around the Chernobyl nuclear power plant.